So guess good to talk about the remaining classes, right? Because we only have 3 weeks to left before we are done. So this today we will finish the hypothesis testing and then probably also finish ANOVA as well. And ANOVA actually have two topics, what's called one-way ANOVA and two-way ANOVA. Uh, and because of time, we just focus on one-way ANOVA. If we have time left at the end, then we'll come back. But that means two-way ANOVA I would not put in your tests or in assignment, neither test and assignment. Uh, but uh, but you will see there's no loss of skipping that because later you will see if you can do regression. Not in this class, but in the second class, actually, that will include ANOVA as special case. So I don't see too much loss about not covering if we don't have time. But if time, we'll go over that. And so our main teaching will be done by the end of next week. So we will be doing ANOVA this class and regression for the 3 classes. And that will means that on the because remember we have a test on the 27th, right? So I mean that so what our teaching will be done on 21st, and 26th will be the day we will review our last year exam and also Q&A if you have any. And then 29 will be no class because 28 we have the exam on the at night. Okay. And later you will see if there enough interest, and we'll see if we can do some Python tutorial in the lab if there's sufficient interest. But if not, then probably but let's see how many people would like to have that. But otherwise, that would be the thing for the rest of the semester. So let's quickly let's finish review of hypothesis testing, and we'll do ANOVA. And ANOVA today, the goal actually is a highly related to a two-sample t-test. It's a generalized idea. Okay. So just to remind you what we have done, right, in the hypothesis testing, right, it's basically we're talking about whether we have sample mean and see the sample mean equal to a certain number, right, or sample proportion, population mean equal to a certain number and population proportion equal to a certain number. And if we know, so let me write down here to help to recall because I think we have too many things to do. So we are checking the I don't know. This pen seems not working very well. One sample, right? You have a Z test, right, and T test, right? And Z test is when you know the sigma square, okay, or you don't know, right? You the sigma square, right? Or you are talking proportion, right? Talking proportion, Z test for proportion. Which was covered in the first part of the hypothesis testing, right? And there are two sample. You also have actually 3 cases we cover, right? So the first is we focus on we don't know sigma square, right? So there will be a t-test, okay? There are 2 cases, assuming sigma 1 square equal to sigma 2 square, right? Then you do under this, you estimate the pooled sample variance, right? And in the case that not, you use different separate variance, but the degree of freedom has to adjust to a very complicated model, right? So that is the 2 things we cover. Okay. And also we have a paired t-test, And pair t-test is saying that for each individuals and you have that in population 1, population 2 is pair, right? So the first 2 is independent sample. The last one is the pair 1. Okay. So after that, today, which we'll continue, we don't have time to talk about, is the same as here, right? The T, right? So this go to this 2, right? And we have a set test, okay, for proportion as well, okay? And these are all for the mean, right? For the mu, right? Or pi, okay? And for sigma square, okay, there's actually something to do, but we don't cover it. It's a chi-square method, but we'll do an F test, okay? There's something can be done here, but we're not covering, okay? But we just do the F test, okay? So that would be the rest of this class, okay? And turn out we will do after little bit review, finish all this, is we'll do this guy, okay? And this guy is talking about you have 2 population, right? And you assume the same variance, and you want to see that different or not, right? Just compare 2 group, right? Whether it's Hong Kong or Shenzhen, right? Compare 2 cities data, right? Or compare 2 different product. And if you have more than 2 product, okay, or you want to compare Hong Kong, Shenzhen, Shanghai, Beijing, right? 4 cities or more, then either you do the t-test many times, right? Or there's a much faster way that is called the F-test, or it's called ANOVA F-test, which will be the main focus of today's class. Okay. And so without further ado, then let me continue the thing we left last time. It's called the Z-test, proportion, and the F-test. Okay. So let me jump to that one. As we finish the review, let's jump to the, okay. We'll basically stop somewhere here, right? So just to recall, as same as one sample, the sample proportion will follow the bell curve, right? Especially when n is large and p is not too small. And it will imply this thing would happen. And since we are focusing on independence, so basically the variances add up together. So that would be the difference between the 2 bell. It's just difference of the mean and sum of the variance, right? So that would be, we know already from what is the meaning of the bell, right? This is a special property, okay? And one of the interesting thing is that if you, under the null hypothesis, okay, if 2 populations are the same proportion, okay, actually we can calculate proportion relatively easily. Why? Suppose you want to say I compare the proportion of people, like say in CHK, right? Whether boys and girls or male or female, well, say for example, do they sleep early enough, right? Do they have enough sleep, right? The proportion of people with enough sleep. Then if you think that the proportion of people having enough sleep is no different between the gender, right? In that case, and actually you don't have to separate them, right? You can just totally looking at how many boys and girls you're asking, which n1 plus n2, and how many people have enough sleep, right? x1 plus x2, right? You don't actually differentiate, right? Because what is pi 1 and pi 2, right? To estimate pi 1, right, the best case is to use x1 over n1, right? So suppose you want to guess how many people, how many boys have enough sleep, right? Then it's x1 over n1, right? This is a good estimate. And to guess 2 will be number of people who say yes, right? x2 over n2, right? So that will be the best, the guess, right? There's these 2 are unbiased estimate, right? But under the case that's the same, actually you can do a better job. I mean, that is both of them are unbiased estimator, just same as what we said. This is 2 unbiased estimator. they can use to guess pi, no problem. Or any combination of that would be, say, half of x1 over n1 and half of x2 over n2. This is a good estimator. Or 1/3 of x1 over n1 or 2/3 of x2 over n2 will be a good estimate. Any combination will work. Right? But you will figure out what is the best combination. Turn out to be this. You just forget about the grouping. Just how many people have enough sleep doesn't disregard of their boys and girls. Just add up, right? So these will be given as the best guess. So is that clear what we're doing? So that would be the idea that you would try to work on is how many on the end is called the p-bar, right? So this is good get the best guess for the pi. So this is the most efficient one. So that's why we learn efficiency, right? It's unbiased, but also in terms of efficiency, this is the best. Okay, which we prove it at the in the some slide later, which is technical, but we don't worry too much about that. But given this, it means the following, right? Unidirectional, right? They're the same. So you would say actually they would follow the same pi. So this is the new thing, right? Because this is something that derived from the null hypothesis, right? You know the bell curve, but you assume they're the same, so they would have the same variance, right? In population, but of course you would change by the sample size, right? If the same sample size, then the same bell curve shape. Because this is the normal, then basically you can calculate the standardized normal, right? By subtracting its mean divided by the SD, which is the square root of that. That is the standard normal. Then you can do the standard method, right? And we're done. Okay, so that is not something too complicated, I hope. Okay, let's go for the example because you will see that actually no different from the one sample case, right? The one sample case would be you don't have this, you don't have that, right? It's the same thing. But okay, now let's see the example and work it out, and hopefully it can convince you this is the thing. One thing to let you know is if you do the confidence estimator, you can't use p-pi, p-bar, because you don't have the null hypothesis that they're the same. So here is a very important thing is you notice this different from the previous cases, right? Previous cases, the denominator of the hypothesis testing will be related to the margin of error in the interval estimator. But in this particular case, they're not the same, right? Because we don't have p-bar over there, right? So that is different from the denominator here, right? Used to be the same, right? Usually this guy is this guy. But in confidence interval, then you can't use this because we don't really know P1 and P2 are the same or not. So we can't have that simplification. So that is a only difficult part that are associated with this. But otherwise, everything is pretty straightforward. And you will see in the assignment that are assigned to you, then it's not something complicated. So let's see this example. Okay, it's I have two set of binary data, right? Just for example, maybe a question of asking whether you like particular, whether they like K-pop, right? So maybe boys and girls are different, right? So maybe a random sample from boys of 30 boys and 60% they like, right? So that means that in this particular example, right, it means N1 is 50, okay, and X1 is 30, right? Of course, right, so that with the idea, right? And you have second case, okay? And with N2 is 40, okay? X2 is 28, right? X2 is how many people will say yes, right? Okay. So that would be the idea, right? So if you ever want to guess, right, what's proportion of population one like K-pop, right, would be just 30 over 50 will be 0.6, right? and you ask how many people who liked, right, would be 0.7, right? So we have that already, right? So that would be the answer to that question. So remember, these P's are all bell curve, right? Bell curve looks like. And the question would be whether they are same or not, right? So again, what we have is like P1 minus P2, right? And under the null, they're the same. So that means that the bell curve would be center at 0, right? And the bell shape like this, right? And you see the answer we have from the data, the difference is actually negative 0.1 because 0.6 or minus 0.7. So it's somewhere here, negative 0.1. Of course, the question would be, we're doing a two-tail test based on H1, right? It's not equal to. So the question would be, okay, would this area, right, times 2 is less than, say, 5% or not, right? The alpha, we can use 5%. We just look at this area, is this small enough, right? So this is our, alpha is our idea of type 1 error, right? And we know this, the shape, right, of this variance, right, will be P1 minus P1 over N1, right? And P2, 1 minus P2 minus N2, right? This is, okay. And we also know that because we are assuming the pi is the same, right? So actually we can guess a much better guess, which is P hat, the P bar, this guy, okay? P bar, this guy, right? So basically just add them, how people like the K-pop with the 58 and over 90, right? That would be our answer, right? So that would be the answer to the question, right? So you can just replace this to the this P here, right? Because they are all, you can replace by P bar, right? And once we know this, right? This is the variance to take a square root, then you can actually calculate the area, right? And if you look at the next page, right, you will see the number, okay, is negative 0.9, right? So that means that if you convert that to Z, right, 0 is here, you get a bell curve here, right? And then 0 is here, right? And what's 0.1, right, will be negative 0.9, okay? Remember how to convert this is just plug in the number here, right? Just N1 you know, N2 you know, P1 and P2 replaced by P bar, and you take negative 0.1 over the square of this guy, right? So how can you do this, right? Just this area, right? This area, same as this area, you will do the norm dot s dot this, right? 0.9 true, okay? Because two tail tests, you can multiply by 2. Yeah. So you can easily see actually the next slide that this p-value is much larger than 5%. So you can't reject this one. So you say that there's no difference between boys and girls in this context. Okay. So if this is small enough, then you can reject. So that would be the main idea. Is that okay? The main goal of this. Right? So that's why you see the p-value is 0.34. You can also do the critical value method. I'm not going to repeat that, but the same. Okay. And you can also see when you do the confidence level, Okay, you are not using the common P bar. You have to use the own P1 and P2 gas. Okay, which is 0.6, 0.6 and 0.7. Right. So this is the only two part that you have to be very careful. And I think I have the I think my assignment already include this case, so you can have fun and check out how can you work out this problem. And comparing proportion is very common, right? Because you want to see how many people like your product, right? Sometimes you can't really ask the number, but you ask yes, no question along survey, right? Would they like your product, right? Because that's very common, right? Because you want to see, say, suppose this is Hong Kong and Shanghai, different city. You want to say how many people like your product, right? Then if they're same, then probably you use the same marketing technique. If not, then you have specialized different city if it worthwhile, if they're different enough, right? So that will actually, you use quite a lot of this technique when you actually do a survey. Because you want to see if you need the same technique or different technique. Is there any question? So that would be the thing we covered. The only new thing is when we do this, we use the P bar to calculate that, right? That is something that slightly different from that. Okay. Is that okay? If there's no, then we go to the very last thing for this chapter, which is the most simple, but yet I think it's the most powerful thing. It's called the F test. Okay. The test by itself is very, very, very simple. Okay. And what we do is look at the two population, again, independent. You want to check the variance are same or not, right? And why you want to do that? First, variance is the idea that in the stock market is the risk, right? So if you want to compare two different stock or investment, are they same risky or not same risky, right? As long as you can assume they follow normal distribution, you can always use the F test to compare, right? You can compare this. The second is, remember the T test. We have two things, is whether the same variance or not, right? There are two formula there. And this test can justify whether you use one or over the other. Okay. And that's why you want to test they have equal variance or not. Third, later we will see today, at the end of today's class, when we do ANOVA, okay, actually we're comparing mean, but at the end we'll use compare variance a way to do the job. Turn out to be very interesting, right? We want to compare mean, but at the end the calculation is we compare variance, which will turn out, let me tell you why we do that at the end of today. Okay, you understand why. Okay, but compare variance is very common. Okay, and there's a lot of uses. The variance like precision or quality control. There are a lot of reasons why I compare that. And the interesting part, it turned out to be, okay, if you compare variance, turn out, okay, we're very simple. You just compare the sample variance very naturally, right? You want to say which variance higher or less than the other, just compare the variance of the sample, right? If this number is super close to 0 or super large, right, then you would favor H1, right? If they are more or less close to 1, right, which suppose under the now is a case, suppose close to 1, right? But if far away from 1 on other side, then you reject, right? Because 1 should be something common, right? And of course, it really depends on the sample size, on the sample population 1 or population 2, right? So that's why the F table would depends on how many observation in the two samples, right? So that's why you need to check the N1 minus 1 and N2 minus 2 table. So this is more complicated than T table. In T table, we just care about one number. That's a one dimension table. And F test, you have 2-dimension table. So you have to make sure that you have N1, but there's nothing when you talk about programming, right? Just another parameter to enter, right? So of course, when you look at the paper, then you have the more complicated tables, okay? But that would be the idea, okay? So just repeat, right? Under this, you want to see S1 square over S2 square. Okay. The shape, of course, depends on N1, N2, but in general, the shape looks like this is 0. Okay. Remember, you cannot go, the ratio or positive number cannot go below 0, right? So you'll be something, depend N1, N2, sometime like this. Okay. Sometimes it just go down strictly. Okay. And 1 is somewhere here, usually, run somewhere here. 1 is somewhere here. Okay. Right. You would, if now it's true to expect somewhere around 1, right? But you reject, right? If something like right, let me use other color, right? You reject if something like this, right? 5% here and 5% there. Okay. And you would see the one of the problem is this F distribution is not symmetric, right? In general, T you can, or the Z is, the bell curve is symmetric. So you assign 5% on both sides, right? So how about F? It's not symmetric. So how are you going to do that? We don't differentiate that. We are still, as classical way is, we would just make 2.5% alpha over 2, 2.5% on both sides. Although asymmetric, we still keep the same tradition because we don't know in advance which is going to happen. So we will have 5% on both sides. Okay. And some of you would ask, does it matter I put population 1 above and population 2, right? Because they're swappable, right? And turn out it doesn't really matter because if you swap, you check different table and turn out the answer the same. So it doesn't really matter what you call 1, what you call 2. Okay, it doesn't really matter. And I think I prove it in these slides. Okay, so let us go to the actual work and see how we work together. Okay, of course, here I use the 2-tail test, but many often you will do 1-tail. Later you will see today the ANOVA, we will do 1-tail. And many of the application will do 1-tail only. But if you compare variance, you don't know which one's bigger, then use 2-tail. But in many application, 1-tail is more common when you're doing some more interesting work, but that's okay. Yeah. And the slightly difficult part is the 2-tail. Okay. When you remember the 2-tail, it is normal bell curve and the T, right? You would 2-tail would be the two-sided test, right? You take the tail area, right, times 2, right? Then it would be, well, you actually, the formula would be you are looking at the area on the left-hand side or right-hand side, right? Look at the minimum times 2, right? Wherever it is, right? Because on the left-hand side, you go to the left, right-hand side, go to the right, right? That means in general, it means that you would take the minimum of the, look at left and right, look at the minimum and times 2. So this is the Y with the formula here. Okay. So let us go to this example, okay? And then you will see how we operate that, okay? So we have an example of N1 equal to 50 and N2 equal to 40. And the sample variance is, for one is 30, the other one 20, right? So you want to say whether you want to text whether the variance is the same or not, right? So in the stock, it will be, right? The stock will be, are the two stocks the same risk or not, right? So remember the F test, you have to, some assumption is normal distribution. This is very important. If you don't satisfy this, then F test is not valid. Okay, so have to be very careful. And I have to emphasize this. I mean, probably you would forget everything from this class after the exam, right? But you have to know in statistics, many of things are dependent on assumption. If you this is not satisfied, then what you're doing is not valid. And probably the question you ask, if this assumption violate, what can you do? You have to use more advanced method. Okay. So this is the thing I have to emphasize because I'm pretty sure you will forget about all the details. Of course, once you learn, you can pick up very easily, right? But the problem is to ask why we learn this if you forget. But once you do it, something in your memory, deep in your brain, then when you need it, you can pick it up. So that's the reason why we still ask you to do a lot of assignment, right? Because to reinforce your learning to keep in your brain. So, but anyway, just make sure that you know. So far in this chapter, we always assume normal distribution. If it doesn't satisfy, there are many other methods to do. Okay, but that will be beyond the scope of my class. Okay, maybe go to other classes to talk about how to do that. Say, for example, there's some bootstrapping method. There are other method as well. Okay, but that is something not we cover in this class. Okay. So if you draw this, right, again, we will have a graph like this, S1 square over S2 square, right? And you will look some F distribution look like this, right? And one may be somewhere here. I don't know exactly, but one be somewhere here, right? Under now is here. If this is too big or too small, then you reject, okay? And if you take the data, which is 1.5 here, okay, 1.5 here. The question is it 1.5 far away from 1 so that we drop our H now, right? So it's always the case like this, right? Because we know the shape is something like that. And is it 1.5 large enough? Then again, our question is looking at this area, okay, and times 2, right? And we are saying, is it going to be big enough, right? So what's this area? This area, if you use the same as what we have seen, we just use F dot T, right? F dot this, right? Because it's 1.5. Why 1.5? Because S1 square is 30, right? And S2 square is 20, right? So that's 1.5 here, right? 1.5. And what you put is you put N1 minus 1. N1 is 50, so you put 49. 49. And what is S? N2? N2 is 40, so it's 39. Okay. Just put, and then you put true. Okay. And remind you that, okay, this is not the answer because this only gives you the error on the left-hand side. So you would take 1 minus. Okay. 1 minus. Okay. And then times 2. That will be the p-value. Okay. That will be p-value. You can calculate that. Right. Or very often we are doing the critical value method, right? So what we're asking is looking at, let me use other color. Okay. We want to use this 0.025%, right? And this is again 0.025, right? Okay. And what the value? Let me see the pen will be useful. The F inverse 0.025. Can't use the pen. 0.025. 49. 39. Okay. Will be the left critical value. And the right critical value will be just F dot inverse 0.975. 49. Okay. This Excel function will give you these two numbers. One is 1.84, one is 0.5. So 1.5 is not in the extreme region, right? Because the rejection region is less than 0.5 or greater than 1.8, right? So your data is 1.5, so it's not within this rejection region. So that means that you can't say they have different variance. They're same. Okay. Okay. If you in the stock market, you would say, okay, these two stock, although historically they're different variance, right? One's 30, one's 20, but you would not say one is more risky than others. Okay. The data is not sufficient to tell you would favor 2/1, right? You can't say. Okay. It can be just due to sampling mistake. Okay. Okay. So this is as I said, the stock market is the most direct application. And later today we'll do ANOVA that would be more direct one. Is that okay? Is there any question before I proceed? Okay. If no, let me end this chapter with Excel. Okay, without Excel. Okay, we'll go over them if there's no further question. If there's a question. So this is the F test. Remember, F test is compare variance. Okay. I hope that's okay. Is that okay? So we will be comparing variance for the F test. Okay, we're done. So let us quickly review what we have done, right? As we have said, right? This is just trying to, if you reverse this, calculate the p-value, but I think already told you how to do it, okay? And this is telling you that if you swap, the same answer will get. There's no difference between the two results, and the p-value is the same. So I'm not going to talk about that. So here is, for the time, I'm not going to go into show you Excel one by one, okay? But I will just still just go into the slide, but you can see what's going on. So this one is called the Z test, okay? And this function actually will be give you the p-value directly, okay? If you give the data, okay, one sample t-test, sample Z test, you given data, which is x, okay? It can be data directly, or you can keep the cell range, right? And you can give the mu, which is the mean you want to say whether you test. You get a sigma. If you don't use sigma, then you use the sample one. Okay, and this will give you the exactly the Z test. Okay, so if you actually have a very large sample, and because very large sample, T and Z are the same, so basically this Z test actually will give you very similar result to T test, right? Suppose your data is more than 200, then I don't see the difference between the C test and T test when we say, right? So this will apply. You can omit the last argument, right? So that's very convenient. And do note that this one only gives you the right tail, okay? So the left tail p-value we have take one minus. If you need two tail, then you have to use the 2 times the minimum of this, the right tail and left tail. Okay, so that is already that will be set in here, right? So the green, so the yellow is my data. The column A is my data, and column B and C, right? The yellow part will be given the input, what is the mean and population SD, right? The alphas. And the green part will be if you really do the shortcut, the t-test, right? And we have two tail with a minimum of the right tail and left tail, just to make sure you know the formula if you want to ever do it. And here will be the blue part is actually calculating from scratch, telling you that how this formula get, right? And this formula should not be surprise to you, right? Row number eight is n is counting of them. Sample mean is average. Then the error will be the standard deviation divided by root n, right? Because that will be the standard D for the sample mean. And then you can calculate the t-test statistics, right? This is simply what we call standardized, which means that this C9, right, the sample mean actually subtract from the population mean, which is C1, right? Basically, this is C number 9 minus C1 divided by C10, okay? So the standardized actually means the first number minus the second number over the third number. That's called the standardized, okay? So this is basically you can replace by C9 minus C1 and then divided by C10, right? So I just use this to do the calculation. And once you do that, you do the norm this, right? We know how to do that. Okay. So this is I hope you can check it out to make sure that you understand all this code. Okay. And then you know what we're doing, right? If you don't understand this code, then you have some problem with understanding. So you have to go back and check, right? Because I think that include every calculation that we do in this class, right? So, and same for one sample t-test, the same idea. With alpha, the mean, with data, right? The sample mean is like this, and we can do all the calculation, right? The t table, okay? And this one, we don't have the c-test. Function applied is telling you how you can operate that in your case, right? So, I mean, once you got the data, you can just apply the function I have, then you can do everything quickly. Okay. I hope you will see how you operationalize this, right? When you actually have the data, right? You have data, you have this, then you can done. Okay. And then we go to two sample tests, okay? And we learn the t-test, we learn three different things. One is we learn the equivariance, okay? So when you have two sample, you have to input two things, right? So that's why two set of data, which is x1, x2, right? So this will give you data number one and data number two, okay? And this all the data there, right? And you will see we have two here, okay? And you ask what two actually is called equivariance. And later you'll see what's there were three options, one, two, three. But number two is called equivariance. Okay? And here we have another argument which is the middle, the third argument. Okay. And this third argument will be this one imply right tail, and this imply two tail. Okay. And you ask why don't they have a left tail? Because they are lazy. So because one mile's right tail is left tail, so they just don't do the complicated job. And two tail already tell you the answer, right? So I hope it's clear. Once you give data, you can easily do it. So that's why I said you don't really worry too much about the calculation, right? Just the Excel, give the data, tell me what kind of test you want, the automatic give the answer, right? So I mean that's something that you are not too much concerned about the formula, but of course in the Excel slides, right, I tell you how you get this formula, right? So I actually show you the blue one. Of course, in the actual practice, you need the green one, right? And the blue one is I show you how you can do all the calculation and prove that the formula we learned in the class is correct. Okay. So I hope at least you know how to do the blue part. Okay. You can try to go to check whether you understand Excel is try to see whether each line makes sense for you. I left it for exercise, but for you have fun. But or during the break you can try to check. If you don't understand, ask me. But you will see how we get that. The only difficult part is the SP square. It will be something like this thing, but it's nothing. But it just S1 and S2 the average, right? Based on the sample size. Okay, so but I hope this is not something too much trouble for you because what you need is just like this guy, right? This is something you have learned already. But I tell you that those trouble you learn can be done in just one single snap and do it done, right? So same now is with unequal variance. So what's different is 3 is used here. Okay, 3 is the thing that you have unequal variance, right? 2 is we have equal variance. Okay, so same idea. Give the data, give me the thing, and then you can do that part, the p-value. Okay, and I show you here how we get that. The most complicated thing you can see in this slide, if you don't use the green, use the blue one, do it yourself, then will be E7 or D7, which is the calculated degree of freedom. I simplify it, but you check. The one I do is actually degree of freedom, which is the T table in the check. It's going to follow that complicated formula. Okay, but already show you that how we can arrive at relatively not so difficult. Okay, yeah, the formula is ugly, but you will check how this is same as what you see in the slide. Okay, but that is the thing, right? That's why I said you don't have to worry about the formula. The green thing is there already. Okay. So I said in the exam, I tend not to ask you to do a lot of calculator. Okay. But in the rare case, I accidentally put a lot of calculation, right? Which you don't able to do it, then remember the Excel function, right? I will give we will give almost all the credit uh, if you write the right Excel formula. Okay, not full credit, right? But almost full credit if you have the Excel formula right, and then you tell me how able to handle that. Okay, and you will see this t-test. The last one will be one. Okay, one with the pair t-test. Okay, so just you would tell them one, then you would just look at the difference, right? Remember, this is paired. So x2 and x1, this list have to be same length, right? Because you will be caring this difference between every item, right? Just care about this, right? Actually, do it. You're doing t-test for this guy, all right? So that would be the idea behind. Okay. So if this is okay, I mean, this is how we can calculate that, right? I think I have somehow missed this average here. Okay, this is just uh, a, average of C2, C7. Sorry, for some reason I don't know why it went missing, but the mean is just average of the column C, right? Because this is the average over there, but because difference for each observation, you can do actually a t-test on that. Okay, so this is the formula there. So lastly, we have the F-test. Okay, and F-test will be just you give me the data, right? I want to see they have same words or not, right? So I give the state the stock return of two stock, right? Give me the that. Ask the F-test, then I can know whether same or not, right? And remember, this is a right tail. So this is a two-tail p-value. Okay, the two-tail p-value. So we can directly know the answer. Okay, we don't have to worry about left tail, right tail. And I already have the uh, telling you why this is the case, right? I just show you the N1, S1, S2, and then do all the calculations. Okay, so you have the time. You can take a look at the blue one to check whether you understand. But there's nothing new in this blue thing, just to operationalize in Excel. But in the application, you do just Python or the software or Excel give you the green thing, right? So, but it's better you know what's going on, right? Just not otherwise you don't know what you're doing. Okay, I mean, uh, if you don't know what you're doing, then you are no better than any primary school student who just able to ask the AI, right? So they can always, if they can do it, what's different, what makes you different, right? You know what's going on. And you see when you apply, when this one apply, when it's not, right? It's important to know this only apply when it's normal. Okay. When it's not normal, we have to go a little bit further to think what can be done over there. Okay. So let's a break. I mean, of course, I have something Excel add-in we haven't covered, but you will not spend more than 5 minutes on that one because it's just the same thing, but use Excel add-in to do the calculation much quicker. Okay. But after that, we will go on to the ANOVA. Okay. So let's a break of 15 minutes and then we come back in 11:36. Please fill in the you reply if you want to know. Uh, let me know how well you're doing. So I hope you're well. Not sure usually from my experience toward the end of semester, we are getting more difficult and then you tend to have more problems, but uh, we are not going to rush anything because we still have enough time. So in case you are having trouble, we'll slow down a little bit and ask me question. We'll answer. Yes, I think didn't the TA release yet? No, no. I asked the TA to release. Maybe you can ask the TA to ask her to release. Uh, it will be released. There's no problem. For sure. I mean, I have no intention to keep it secret. So, I mean, every year I release answer to the assignment. So yes. Um. If you the easiest thing is you email a TA and forward me, then you'll be released very quickly, right? Then you should be if you want it to be quick. Otherwise, our TA may be tired, super tired. Oh yeah, I do agree because at the end of semester we are all super tired, and that's why you will feel the material increasingly complicated at the end of semester because of both your situation and the class material getting more complicated. Coffee or milk tea? I have very strong coffee, fully roast. I often have that when I in the middle of teaching. I just need something to make myself more refreshed. And my office have many chocolate, the wing drink, the liquid one and the solid one. So I keep myself awake. But of course, it's better to sleep earlier, have enough sleep, and drinking coffee is a short-term solution. Uh, some of you may ask, do I have Red Bull? I do try a Red Bull because, but when in the US, but I did try it, but I can't sleep whole night, so that's why I don't dare to do it again. And another thing I remember I did once is I have a four sort of espresso in one coffee. After that, I also can't sleep at night. They call in Singapore, they call it the prime espresso. Just have four sort of that. That would be also super crazy. So you can try if you are super tired, but I would recommend actually you take a rest. Okay, that is better because efficiency concern because your brain is still growing at this moment. Surprising to you because you would have thought that your brain has to stop, but actually at every moment of time, actually until 60, before 60 years old, actually the brain is still growing. So so just have enough sleep to make your brain grow a little bit. Otherwise, not very good. Will Excel function exam? Yes. The answer is yes, right? The Excel function yes, because sometimes I can ask you to calculate, so I ask you the Excel function. But remember, you bring everything in your exam theater, so I don't think you would be too nervous to figure out where it is, right? Uh, but the answer is yes. I mean, you can see my previous year question. I do ask Excel question, right? Especially you can look at if you ask actually you didn't read, you haven't you're not that nervous, right? But if you ask actually this question, look my last year paper, exactly the very first question I asked. What is the I don't ask you to calculation. What is the Excel input to calculate the sample mean and sample variance? Okay, I actually ask. So if you ask, then you haven't tried to read that, but it's okay. We'll go over this when I on the 2 weeks later. Okay, we finish everything. We have time to go to that. But I think we have time. Don't worry. We'll go over that. So there's a question. No, okay, that's good. Oh, surprising. Someone think is first day and Friday. I'm pretty sure these two are the one that who said they are. I know who the guy is a super tired and a tired person. Must be these two, I guess. So I hope you're okay. The weather. Someone said cloudy, sunny. Okay, that's good. No one said rainy. So we're still in the same universe. F test to compare wins. That's very important. That's something we do. And then C test Excel. What does that mean? The key point is you're sweating. Someone learned hard. Okay, that's good. You learn to have golden heart. That's good. But not sure is it useful for our cars. But that's good. Speed is okay, not that bad, and you're okay at following. But but you will do the assignment. Remember the assignment. So I've outlined here. I'm not sure this is they intend to write 5, but they write 1. But maybe he's super tired, so that he taking this one. But a worrying side, you have more than half of people is more tired. I mean, in the other section, more evenly, maybe 30-something, 30-something. So our class is more tired, which makes sense. It's a Wednesday. So Monday, people are less tired. Wednesday, people are the most tired, I guess. Because tomorrow you are going to be Friday, it will be soon. And Friday is a Friday's day. So Wednesday is almost always the most tired day, for sure. Yeah, really tired for late November. Always the case. I mean, not just you, also your teacher. Everyone's very tired, right? Because I also make the exams and also grade everything and make sure everything is all right and well done. So not just you, everyone is very tired. Okay, but if you think it's too tired right now, then prepare yourself when you go to the job market 2 years later, especially those who are in accounting. You know that your whole life is like this forever until you get retired. Okay, actually, because my wife was working in big four, right? And then when it's a peak season, it's like working like hell, right? In the normal season, it's okay, but otherwise, I mean, normal season you prepare for the exam, right? In the peak season, you just work like crazy, right? And so you will be November every day. Okay, hopefully you are used to that, but your table, yeah, you bring everything, so I'm not going to provide you table because you can bring your own table and don't need to my table. Okay. And remember, in the worst case, just use Excel function to write your answer. Okay. And then assume there's a number in Excel function you can write. If this p-value based on the Excel function more than 5%, what you do, less than 5% do, then we'll try to give you full mark as possible. Okay, as long as you tell me how to work with Excel. All right. We'll try to, as a TA when the grading, try to give the marks whenever we can give. Okay? Of course, wrong we can give, but whenever is okay, approximate, we try to give you as much as possible. Because none of you are competing with each other, right? All of you are competing with the grading rubric, right? How well you're presenting yourself. So I don't see any exam tips. There are several things, several tips. One is please make sure you know your past paper well, right? Because that's the same as all the exam, right? Some of you know, right? Your college entrance exam, right? Same as the thing, right? The DSE, all the exam, right? Our past paper will be very useful. Is right? If you learn statistics, you know, past paper is unbiased estimator and also the most efficient estimator for the future exam, right? Because how I think is limited, right? So you can look at how I make the past paper, then probably you give you idea what I'm asking. And also exam is try to test the knowledge that's the most important, right? So that's why do the past paper will be good, right? If you have nothing to do, you can do past paper for my class or other class as well, also work, right? But also we have quiz as well, right? Self-checking quiz, please do them as well. So because that would be very useful. And then make sure that you know your assignment, right? You ask the TA to release the result of assignment. That will be, you know, the answer of assignments, then will be great. And also the last thing, maybe you look at the green boxes for our class, which operationalize all the theory part, right? You know how the green part we've done, then you should be fine. And then, of course, very last, you just look at the lecture notes and should be no problem. Okay. And I think the next Thursday, not this, but next Thursday, we have a tutorial section optional, which you can ask question. So make sure that if attend on in person or by Zoom would be good. Okay, just make sure. Or if you have question, please feel free to ask. We will section 2 weeks later from today. Okay, so make sure that you just utilize all this material the best for you. So the tips. But of course, I understand you have so many other classes. My classes seems to be very easy, so probably you would put it the least time and least effort on that. But that can be a mistake because our course has actually 4 credit, right? So please spend the appropriate in proportion to the credit, right? At least you spend 1/3 more effort compared to other classes. I think you spend a lot of effort in accounting, right? So at least spend half of the amount, right? If not more than that, right? At the same amount of effort on that, right? Because our class is not that complicated. It's open book, right? So just make sure that you do okay. And your project, I think the project is the thing, right? Spend the right amount on that, right? Don't give me some very lousy project. I just ask you how many pages, right? Saying one A4 paper. Okay? Do an appropriate job on that one, right? You spend at least as the same effort on your assignment, right? Don't just randomly give me something not so good, right? Even if I want to give you good grade, then it's very difficult, right? Um, yeah, that's so be it. Okay, so let's quickly finish the uh this one add in, right? Um, this add in is just telling you that we have these three things, the t-test, equivariance, not equivariance, okay? And for example, if you use the add-in, okay, just make sure that you know what we're doing. Add-in will be just Excel here. If you do window, will be file, options, and then add-in. I mean, we do that in the chapter 1 already, so make sure that this NS2 pack is clicked in. If you don't know how to do in the Mac, then ask the AI because I don't own the Mac, so but AI would help you perfectly how to do this add-in. Once you do that add-in, then you go to data analysis, okay, and then it will show you uh, this last three. Okay, we will use basically these three. Okay, but this three actually no different from the t-test you see already. Okay, so uh, but so this, if you do this, right, just tell them what is the x, what is the y. You tell them under equivariance, what do you want, right? Usually it's 0 here, right? The difference, the, the mean of the two population. Then you put alpha 5%. Then you tell them where to put in, right? Just like in this particular example, right? So just tell them um, where is the data, right? Which is column A and column B. You have labeled there the 0 and the alpha is 5%. Then give you the result. Okay. So this is something usually you actually do when you do Python or R package, or actually you use ChatGPT. You can tell them this; they will give you this table. Okay. Actually, ChatGPT can do that as well. I mean, you give the data, and then ChatGPT will give you this result. Okay. But the important part is they give you the DF and T stat and the P value critical, right? So basically just check these two number and you're done, right? But other thing, actually, you understand every single thing there, right? Every single entry, you should be able to understand, right? So that is the meaning of this class, right? Try to make sense of this output, right? And then same for you when you try to use AI or any software, right? And if you assume an equal variance, they're the same, you enter the same thing. The only difference is everything the same. The input the same, A and B, and label this is 0, and you have to put 0 here. If you don't want anything 0, and same, you have one tail or two tail. The only thing is a little bit tricky is here they give you the left tail. Okay, but surprisingly, in the t-test Excel function is a right tail. So I don't know who designed this, but your head have to spin a little bit. Okay, I don't know who is that crazy, but this is how they design the program, right? The t-test Excel function is a right tail, but here is the left tail, so your head have to spin a little bit. Okay, make sure that you know what you're looking at. Okay, that also explains why when you look at different across software in R, Python, data, whatever thing you are using, that you have to look at the menu when you check because you don't know what they're giving you. So that's why you have to learn statistics, right? Otherwise, a primary school kid can replace you easily, right? And that's why, and the pair test the same, right? You get the pair, okay? It's the same idea here. Okay. And this F test above, you do the same. Give you the range and then give the output there, give you the critical value. Same idea. Okay. So basically, this is just do the same thing, but just lists out everything very nicely. And this is something you expect, as I said, if you do any software, Stata, R, or whatever, this is the thing to give you. Is that okay? So I don't want to bother you too much with the Excel because you know just all the number there. Okay, there's nothing new except they calculate everything in a one click, boom, and then you're done. Okay, we're happy. Okay, so now what we left is eventually go to a very exciting thing. It's called ANOVA, which is called in this topic is called ANOVA is analyze of variance. It's called ANOVA. Okay, ANOVA. So what is this guy exactly? Okay, this is as old as World War II. I think it's 1930s and 1940s. They invented to understand, say, actually application in farming. Okay, you can imagine there are many type of farming application, right? You would try to grow a plant, grow a crop, and try to maximize the crop by varying different amount of sunshine, different amount of water, different amount of fertilizer, right? And probably you want to see which one will grow best. And the thing, of course, you imagine I can do a t-test for each scenario, right? T-test for condition 1, t-test for condition 2 and 3 and 4 and so on, right? Which were natural. But then become very tedious, right? Because how many combinations you need, right? It's NC2, right? Yeah. 1 and 2, 1 and 3, 1 and 4, 1 and 5, and 2 and 3, and 2 and 4, 2 and 5, right? It's NC2, right? Because for every element, you pick 2 of them, right? Then the t-test can go crazy. So turn out they figure out that, okay, you can do one thing, you can do just one F test, and you can check out whether they're same or not. Because you were going to check a lot of things, okay? That is the reason is the ANOVA is basically a generalized t-test. Okay, a t-test of comparing two population under the same variance is comparing two group, boys and girls, Hong Kong and Shenzhen. But now, if you have more than one location, you compare Hong Kong, Shenzhen, Beijing, Shanghai, Tokyo, so on and so forth, right? If many different, you can still do that. Okay, and turn out that these t-tests will surprisingly become f-tests. Okay, you're supposed to do t-tests across between 2, but if you're many group, actually doing f-tests. I'll explain you why we do that, but that's what we're trying to do it. Okay, so we'll focus on what we call f-tests. Okay, we'll call the one-way ANOVA. Okay, and I will not do two-way ANOVA because of the time. But one-way ANOVA is something not too complicated. You will see. Okay, so here is the thing that each observation, I not only observe the number you want to know, but I also have the grouping information, like Hong Kong or Shenzhen, location, or gender, boys or girls, or country or age group, right? So these are grouping. So these are all categorical variable, just grouping. Okay, there's no meaning there. Okay, and you ask, what happens if age group is not the grouping, but rather I have the exact ages? Okay, in that case, we will do regression, which will be next class. Okay, we're studying whether groupings are related to the variable. Okay, whether the mean of different group are different or same. Okay, suppose you're talking about product marketing, right? You're talking about how they're going to pay your product. You want to see whether different age group actually different. Okay, but of course, if you don't say is older people appearing to pay more, is it any function related to that? Then we'll talk about a regression. So we are here. We only interested in the grouping are categorical, which means that the group A and group B can swap the ball. It don't have any meaning in sense of there's no meaning in the group. But if you had a meaning in the group, then we will talk about regression, which will be the last 3 classes we cover. Okay, so that would be the idea. So what's the data you have? The data you have is for each observation, as I said, you observe the number, which is xi, maybe how much they want to spend on a product. G1 is a grouping. It depends on, say, if this is a, say, country 1 or country 2, okay? So the grouping will be any of the C different value, right? G1 may be Hong Kong, G2 may be Shanghai, GC may be Singapore, right? There's a C different types, okay? So this is all one-way ANOVA, which means each observation will only have one grouping. In two-way ANOVA, we don't cover, maybe each observation will have 2 categorization, right? One may be country, the other may be gender, right? Maybe Hong Kong girl, Hong Kong boys, Singapore boys, Singapore girl. But we will not talk about two-way ANOVA because of the time. We just focus on one-way ANOVA. Okay. For the interest of time, we just skip that part. If we have time, we can come back. So the data we got is usually in this way. So each row is an observation. So row number 1 will be telling us how much they want to spend your product, and we will tell which grouping they are. So it can be anything. This is the data you got. Okay, just representing this list of number. Okay, is you group them in the long form. Okay, this is usually the data you get from the database, or you ask to do survey. Okay, so here is another way to write the number, because this will help us to do the calculation more easier. And this is usually the way that you would collect it, do the calculation in Excel. Okay, and it's like this: is you would have the X using 2 subscript. Okay, and you have a 2 subscript. Is actually, when you learn this thing for new, is very challenging. So you have a number, and you have 2 subscript is I and J. The first subscript means which group you're in. Say X1 maybe 1 means Singapore or Hong Kong, the city, right? Or the grouping. Female or male, right? Or so on and so forth, right? And the second one will present the observation number in the group, right? So this means this is the first observation in Hong Kong, right? In X12 will be the second observation for Hong Kong. And X1N1, which you saw in the slide, will be the last guy in Hong Kong. Okay, so if 1 is Hong Kong, so this is the first guy in Hong Kong. This is the last guy in Hong Kong. Okay, and suppose the last city may be Shanghai, so this is the last guy in Shanghai. This is the first guy in Shanghai, right? I and J, right? And N will be sum of the number of people in the group. Okay, so you will see this is the notation we use. Okay, and this is very common. It's not invented by me. This is all the stat book that use it. Okay, and you will see. Okay, this is why we do that. Means that we don't have 2 numbers. We don't have X and G, right? So we just have one list that make our life easier to describe. Okay, of course, okay, you can keep what we have, but this is the notation. And how you present it in the Excel. So this is data that actually you use in Excel like this. Okay, each column will tell you which city, right? G1 says Hong Kong. Okay, so you list out. This is the first guy in Hong Kong, second guy in Hong Kong, and last guy in Hong Kong. Okay, and remember this last group is Shanghai. This is the first one in Shanghai and last one in Shanghai. Okay, and I didn't write the same length because they can be different. Okay, you don't have to have same number of people in Hong Kong and Shanghai. Okay, so it can be very general. Okay, different group. Okay, so remember ANOVA, right? The farming will be a different combination of the way you cultivate the crops, right? Different combination of water, temperature, sunshine, fertilizer, humidity, and many things. Okay. Now, here we will, because of the way that is invented in the, as I said, as old as World War II, at that time, right? People all look at the bell curve, right? So basically, you are assuming that each observation coming from the bell curve, okay, and the bell will depend, the location of the bell would depends on which group you are in, but they're same variance. Okay, so as I said, this model is an extension of the t-test with equal variance. That's what I said, right? Each different group have same sigma square. Okay, I don't have sigma square I, so it's the same group. Okay, what does that mean? It means the following. It means that if you look at data, I have a number line here. Okay, that means that if you look at group number 1, say in Hong Kong, say the group look like this. Okay, the bell curve. The mean will be mu1 here. Okay, and say the last one with Shanghai, we have the same shape, okay, but just different location, say mu of C, right? Another group can locate differently, right? So maybe mu2 is here, okay? Okay, just have the same shape, okay, have the same height, but just different location, okay? So this assumption, of course, you will ask, is it a legit assumption to apply into all the contexts? I don't know, okay? But this assumption we have to make in order to compare, okay? Is it valid? If valid, it's good. If it doesn't valid, then you need other way to handle it, okay? And of course, how can you check this? You've done the F-test already, right? You can do F-test to see whether this valid or not, the same variance or not. But in general, that's we assume. Is that okay? So this is the model. Okay. Later you will see what we try to do is to see actually these mean are all the same or not. Okay. The idea is whether mu1 equal to mu2 equal to mu3 up to mu c are the same or not. The same mean or not, because we want to see as an agriculture application, we want to see a different way to cultivate the crops are different or not. Or application in the marketing, right? We want to see different cities, the consumer will spend your product are same or not. If the same, you can use the same marketing technique or even the same product. If they're different, then probably you cater different market accordingly, right? So that would be the idea. Okay, is that okay? Is that okay? This is the behind say the t-test equal mean just only have 2, right? This is the thing we do just before the break or previous classes, right? You just have 2, right? Equal variance, right? But now we have more than 2, can mean many. Okay, so we want to check whether these mean are the same. Okay, this is the goal of ANOVA, checking if they're same or not. Okay, checking. Okay. And we will do F-test to do it. And very often we can write this way because of normal. This is the way that you often see in the way we decompose it. So this is normal. Okay, this is normal, right, with mean mu I, variance sigma square. Okay, you can take away the constant part, okay, and add the zero mean bell curve there. Okay, what does that mean? It means the following, right? So we have a xi have mu I here, right? This is xij, right? Okay, I can not consider this guy, but rather we can go to 0 at the same thing. This is called mu I, epsilon ij. Okay. Have the same shape, and this you move a little bit, move the mu will give you this guy. Okay, so that's why this is the very often technique. When normal, we can write in this way. Okay, so this is something very standard. You will see very often when you go to the finance classes and all the static classes. Always when it's normal, you can always decompose in this way. Not necessarily true for any other distribution, but normal, you can always do that. Okay, you can always decompose a random variable. If not 0 mean, you can decompose in the constant mu part and the non-constant part. Okay, sometimes this is called the Gaussian white noise. Okay, the epsilon ij, they call it the Gaussian white noise. Okay, but you will learn when you actually see that. Okay, but this is the technique we're using. Now, once we have that, then we'll introduce some notation, okay? And before we do ANOVA, okay? So first is the overall mean, okay, which is the mu, okay? Mu is just mean over group mean. So adding all each group, so the mean of Hong Kong, mean of Singapore, and up to mean of Shanghai, and divide how many city you have, right? This is grand mean. Okay? And here we call this mu I minus mu is called the treatment effect. It's just the difference between each group over the overall group is called alpha I. Okay. Why we need that? Because we want to express in the following way. Okay. So these are all the numbers, right? Mu1, mu2, mu3, right? And the grand mu overall mean, what is the mean of the means, right? Is exactly the middle, right? The mean is what? Mean is, look, the left-hand side, right-hand side are the same, right? So that means that the mu is located in the way that you go to the left-hand side, the distance, same as the distance to the right-hand side, right? So the distance between the sum of the pink is equal to the orange in the middle, right? And that exactly means that alpha 1 plus alpha 2 equal to alpha 3, right? And the F test, or what we care, the ANOVA, is trying to see if these all alpha are 0. The group has no meaning or not. The grouping has meaning or not, right? Because we want to see they're different or the same. So when we say whether mu1, mu2, mu3 equal to mu, it's same as alpha 1 equal to alpha 2 equal to alpha 3 equal to 0. Okay? Is that okay? So that is the goal. And as we said here, okay? So before we do that, we want to guess what is mu1, mu2, mu3, because they are number we care, right? With average people want to spend in Hong Kong and Shanghai or Singapore, and also, right? So X bar with overall grand mean means that all your customer, how much they want to spend on average on your product, regardless of the city, right? So that means that the notation is adding all up, right? So what is this notation? Double summation is adding all the cities. Okay, for each city, you add everyone in that city. So this basically this is what I mean, adding everything up, right? And over what? How many people in your data, right? Overall, okay, regardless of the city, okay. And this means X bar I is looking at a particular city, I, maybe Hong Kong. You're just adding up how many people in a city, how many they spend, and how many people in Hong Kong, right? So that would be the idea. Okay. Focus on the group, right? So it means the following. Okay, just go back to this data. Okay. X bar is adding all this up divided by n, right? So this is X bar, right? Adding all the data divided by, right? Divided by n. N is the total number of the data. And adding all this up will give you X bar 1 divided by n, n1, right? If you look at the average of this, will give you X bar 2. Okay, so that is the meaning. Okay, what is the meaning of X bar and X bar I? Okay, and without any doubts, right? They are all the unbiased estimator, right? So, but let's quickly go into the calculation, right? So if you look at this data, you add up everything there, divided by how many data of them, then it's X bar, right? If you look at this number divided by 4, add up together, then it's X bar 1. You add this thing divided by 4 is 5, right? You add all this divided by 4 will be 5 as well, okay? So this is how you get all this mean, okay? So that should be okay. So for the next, as I said, right, we want to see whether these mu are the same, right? So whether all the sample mean there are they the same, okay? or what the alpha are the same or not, or zero or not, right? So that's I mentioned already in experiment, right? If you don't want to apply to crops, you can see you have new drugs. You can see you have drug A and drug B, how you combine different drugs, right? To make the patient recover the fastest, right? And also the marketing, right? Your different countries same or not, okay? Turn out that we will use the F test, okay? So the main idea of this is use what we call we actually compare variance of different group, okay? So it will involve some calculation, okay? But let me end with this slide. We'll talk about the calculus of variance very soon. So the main idea of this is we have these three numbers, and these three numbers are actually closely related to the calculating variance, and you will see this is the numerator part of the variance, right? Because say for example, the first one is actually calculating variance, right? The numerator, right? If you actually you forget about the grouping, right? You want to calculate variance. This is the first step you want to do, right? You look at the overall mean. Okay, each observation minus overall mean, right? Look at each then this adding up, right? So this SST is sum of square total, which is you would calculate the variance up till you divide it by n minus 1 with the variance, right? The overall. We forget about the grouping, right? Look at all the data, you subtract overall mean, right? That will be the variance. Okay, later you will see. Okay, this is when you divide it by n minus 1, this is called the MST later, which we'll define next class. Okay, you divide it by m. This is a variance based on the total. Okay, and the next one is you calculate variance only between group. Okay, what we're going to do is same as before, but instead of using each individual data, you replace it by the mean of that group. Okay, the mean of that group. Okay, you calculate the SSG. Okay, and if you divide it by n minus c, you divide by c minus 1. This is MSG. Okay. Lastly, you have this SSW. Is instead of replacing this first guy, you replace a grand mean. You replace by each group. And you replace by n minus c. This is called MSW. Okay. And turn out that these three numbers are related. SST equal to SSG equal to SSW. Okay. So what actually this three thing means is the following. Okay. Why they're the same? Let me end with this graph. Okay. Look at data. Okay. If you look at distance to the grand mean, this is called the SST, right? From each data to the total grand mean. Okay. But you can do it in other two-step way. Is you go to its group mean. Okay. You calculate the variance. This is called SSW. If you from group mean to the total, it's called SSG. Okay. So end up this is same as this two. Okay. So at the end, in the next class, I'll talk about what we're actually doing is comparing the variance of these two cases. Okay. And if there are no difference between the mean, they are the same. Okay. If there are difference between location of the mean, the SSG will be much bigger than SSW. Okay. And that is the variance-based comparison. We'll talk about that on Friday. So I don't want to take more time. I'll see you on Friday. Okay. But that will be the idea. Okay. So I see you on Friday. So good luck. So don't worry, we will review this part, okay, in the next class.